So, have you ever really thought about how a star is born? And I'm not talking about just any star. I mean the massive, super bright ones, the ones that are basically the element factories of the universe. It's a huge deal because understanding their story is, well, it's key to understanding our own. And it turns out the clues aren't just out there in space, they're written in the molecules themselves.
And this isn't some far-off, abstract thing. No way. This quote here points out that the evidence is right here, in our own backyard, cosmically speaking. It's hidden inside meteorites. I mean, think about that. These ancient rocks are carrying the chemical fingerprints of massive stars that lived and died long before our sun was even a thing. So we are directly, physically connected to all this.
Okay, but that brings up a pretty massive problem, right? These stellar nurseries, they're thousands of light years away. And on top of that, they're wrapped up in these super thick clouds of dust and gas. You can't just point a telescope and see what's going on. So how in the world do astronomers piece together the story of a star's life, from its very first spark to its big debut?
Well, the answer is it's so clever. They don't just try to look through the cloud, they read the chemistry inside of it. It's like they figured out that certain molecules act like a giant cosmic clock, ticking away, marking the passage of time in these stellar nurseries. It's amazing.
Yeah, this whole idea is built around something called chemical evolutionary indicators. Sounds complicated, but the concept is actually pretty straightforward. Just think of it like this. As a star-forming region gets older and hotter, the kinds of molecules you find and how much of each you find, it all changes in a really predictable pattern. So by measuring these molecules, we can basically look at the clock and tell what time it is in that star's life. It's a chemical clock.
And this diagram, this is our roadmap for the whole process. You can see it's basically a life in 3 acts. It starts with this cold, dense core, kind of the quiet before the storm. Then, boom, a protostar ignites, the furnace kicks on. And finally, you get these brilliant new stars bursting out, totally changing their cosmic neighborhood. This is the journey we're about to take step by step.
All right, so let's break it down. We're going to walk through each of these 3 life stages. It's like we're traveling through time, from the super quiet beginnings all the way to the spectacular grand finale of a star's birth.
And what's crazy is that this whole journey happens in what is, cosmically speaking, the blink of an eye. That first stage, the high-mass starless core, that lasts for about 10,000 years, which sounds like a long time, but that's about the same amount of time since the end of the last ice age here on Earth. Then you have the protostar stage, which can go for 100,000 years. And then, in a final, brilliant flash, the new star is born.
So, Act 1. It all starts in the deep, deep cold. A high-mass starless core is this frigid, dark, and unbelievably dense cloud of gas and dust. We're talking temperatures of just 10 to 20 degrees above absolute zero. It's here, in this absolute silence, that the raw materials for a brand new star are slowly coming together.
And this slide, wow, this just captures that transformation perfectly. On the left, you've got something like the Snake Nebula, a dark, quiet cloud where it all begins. Its chemical signature is super simple, just a few molecules hanging around. But then, look at the graph on the right. Every single one of those peaks is a different molecule. When that star ignites, it's like a chemical factory just switches on, producing this incredible forest of new molecules. It's a total chemical makeover.
And that brings us right to Act 2, the warming heart. A protostar has now ignited deep inside, and its heat is warming up the gas around it to over 100 Kelvin. Now this is a huge moment. It's like a cosmic spring thaw. All those ice-coated dust grains, they start to release their molecular cargo, creating this rich, complex chemical soup. Everything starts to get a lot more interesting.
And finally, we get to Act 3, the brilliant finale. The newborn star is now so hot, so powerful, that its intense ultraviolet radiation literally blasts its way out of that dusty cocoon. This creates this expanding bubble of super-hot ionized gas, it triggers a whole new kind of chemistry, and it even starts to break down some of the bigger molecules that formed earlier. The star has officially arrived, and it's changing everything. Okay, so that's the story. It sounds great, but how do we know it's true? Let's get into the evidence. We're going to look at the specific molecular signs that astronomers use as proof, the clues that tell them this is really how it happens. All right. The first huge piece of evidence is something called deuterium fractionation. All deuterium is just a heavy version of hydrogen. Now here's the cool part. In the extreme cold of that first stage, chemical reactions actually prefer to use this heavy hydrogen. So the molecules in the coldest, youngest cores get packed with deuterium.
It gives them this very distinct chemical fingerprint that screams, "I'm brand new."
And here it is. This is the smoking gun, right here in this graph. Look at that. The deuterium ratio, our chemical fingerprint, is sky high in that earliest, quietest stage. But then, as the star evolves and the whole area warms up, that ratio just plummets. This is our chemical clock, ticking away, giving us a direct measurement of the age of that stellar nursery. It's incredible proof.
But that deuterium clock isn't the only clue we have. As the star warms up, something else amazing happens. You get this rise of complexity. That protostellar phase isn't just a warm soup, it's a full-blown chemical factory, churning out a huge variety of what are called complex organic molecules, or COM.
And this is where it gets really mind-blowing. Astronomers aren't just finding simple stuff in this cosmic factory. They are finding prebiotic molecules, the actual building blocks of life itself. We're talking about simple sugars, acetic acid, which is basically vinegar, and even urea, a key molecule for life here on Earth. And get this, they've even found ethyl formate. That's the molecule that gives raspberries their flavor. The ingredients for life are literally being cooked up around brand new stars.
So you can see this is way more than just some neat astronomy. This research has really profound implications for how we understand our own place in the universe. Because by learning to read this cosmic chemical clock, we've basically built ourselves a time machine. We can look at a stellar nursery today and reconstruct its entire history. And since our own sun was almost certainly born in a similar kind of place, this gives us a remarkable window into the past, a glimpse of the chemical cradle that our own solar system grew up in.
So here's the big takeaway. The complex chemistry happening light years away, that's not just their story, it's our story. It is our own chemical heritage, written across the cosmos.
Which really just leaves us with this incredible question to think about. We've found the ingredients for life being made around other stars, so what other secrets about our own origins, about the origins of life itself, are still out there, just waiting for us to discover them in the vast chemical laboratory of the cosmos?